Hi, today we're going to talk about significant figures, often abbreviated as Sig Figs. So if you've ever taken another chemistry class in the past, you might have hated significant figures. I certainly did when I was in high school, taking high school chem. I thought it was a completely arbitrary system with no meaning in the real world. Boy, was I wrong. Now that I'm an analytical chemist and I worry about these things, I understand that significant figures are our way of indicating how precise our measurements were. Let me give you an example. You are driving a school van on a field trip, and you're going to go down to Randall, Washington. That's where you're going to refuel the tank before you head off to Mount St. Helens. So you need to know how far you drive before you refuel. And so when you get to Randall, you look at your odometer to find out how far you've traveled so far. So this is what you see. You have two options. First is, what happens if you were smart enough to reset the trip odometer before you actually left campus? Well, this trip odometer says 90.8 miles, so that's what you're going to record as the distance. Okay, so what if you didn't have the presence of mind to reset the trip odometer because you were too busy making sure everyone got into your van and put the stuff in the back of the van and all that stuff? Conveniently, you look back in the mileage log and you see that the odometer was at 14,910 before they turned the van over to you. And so you can subtract 14,910 from what's on the actual odometer of 150,001 mile to give you 91 miles. So when we talk about significant figures, what we're talking about is the number of digits we write when we're reporting a value. And that tells us the precision of our measurement. The two scenarios we had before, one was 90.8 miles, the other was 91 miles. Now, if we look at 90.8 miles, we can count up the digits and we can see that's three significant figures. And 91 miles, that's two significant figures. Now, are they the same? Well, not necessarily, right? Because 91 could be rounded off from 90.8. But it also could be 90.7, 90.6. It could be more than 91. It could be 91.1, 0.2, 0.3, 0.4, and so forth and so on. Right? There's a whole bunch of possibilities. And so the measurement of 91 miles is actually less precise than the measurement of 90.8 miles. If you had a really old clunker that you were driving and you wanted to make measurements with your trip odometer, you might be able to get even more precision because you might have an analog trip odometer. With analog devices, you can always estimate an additional digit compared to what's actually shown on your device. So in this particular case, we have 9 point something miles. And if you look at this last thing, that is somewhere between 9.4 and 9.5 miles. Is it exactly halfway between 9.4 and 9.5? I don't know. I think it's a little closer to 9.5 than 9.4. At least the 4 has mostly rotated out. I might think it's 9.47. So that's most of the way to 9.5, right? Other people might think it's 9.46, 9.48, 9.49. But no one's going to say it's 9.42, right? Because it's most of the way to the 5. Now, you might never actually drive a car with an analog trip odometer, but you're going to be using a graduated cylinder in lab, and those have analog markings. And you can estimate additional digits between the markings on your graduated cylinder. So this is really important to know for chemistry. So back to our number of significant figures. If you ask someone who is driving a second van to Randall how far it was up to Randall for them, and they said it's 90.81743 miles, you might think they were crazy, right? Because how do they know that to that precision? They don't. And this is why we care about significant figures in chemistry, because we want to know how precisely you were able to measure what you measured. Okay, so let's look at some examples of how many significant figures are in something. Okay, so this is 63 kilometers. You count the digits. There are 2, so that's 2 significant figures. How many significant figures in 63,000 meters? Well, 63,000 meters is the answer you would get if I said, convert 63 kilometers to meters. you might not have actually measured how many meters there were in the 63 kilometers. You probably just multiplied by 1,000. So this actually only has two significant figures. Those zeros don't count. So people are often a little fuzzy as to how do I know when something counts or when something doesn't count? It's very easy. Put it in scientific notation, and that will tell you 6.3 times 10 to the third meters. Okay, here's another example. Here we've got a really small mass. And once again, I'm going to use my trick of converting this into scientific notation. So 6.704 times 10 to the minus 10th kilograms. So how many significant figures does this have? It does have a 0 in the middle between the 7 and the 4. But if you take out that 0, 6.74 is not the same as 6.704. So that 0 means something. It helps us know what the actual value is. We can't discard that 0. So that 0 counts as a significant figure. This has 4 significant figures. Now, the hard part of sig figs for most people is figuring out the sig figs that are associated with an answer after you've done calculations. So I'm going to give you 3 sig fig rules now. The first one is for addition and subtraction. And this one is different from most of our sig fig rules because we are only concerned with the numbers after the decimal places. So the final answer is going to have the same number of decimal places as whatever your measurement is that has the smallest number of decimal places. Now, in order to understand why this is a thing, let's look at a subtraction problem. So if you were given the subtraction problem when you were in elementary school, what did your teacher tell you to do if something did not have the same number of digits as something else in the problem? Mine told me to write a 0 in there, and then you could do your subtraction and you got 1.1219. But the first sig fig rule tells us that we can only report the smallest number of decimal places that's available to us. So the first number on top has 3 decimal places. The bottom number has 4 decimal places. The smallest number of decimal places we have is 3, so we're going to report this as 1.122. Now, why is this true? Well, remember, we had to put that 0 in there that wasn't there before. And when you're dealing with pure numbers that have no basis in reality, which is usually true in math problems in elementary school, that's perfectly fine. 1.329 does equal 1.3290. But if you're talking about measurements, that's not the case, because this could actually be 1.3289, 1.3288, 1.3287, or something higher than 1.329. It could be 1.3291, 1.3292, 1.3293. We don't know what that last digit actually is. All we know is it rounds to 1.329. And that's why we can't report that last decimal place. We don't know what that last decimal place actually is. Another example, here's an addition problem, 2.47 plus 0.7846. Put it through your calculator, you get this. Always put it through your calculator before you round to the number of sig figs. So we have 2 decimal places on top, we have 4 on bottom. We can only report 2, so that's going to be 3.25. All right, our second sig fig rule has to do with multiplication and division. Here, we're going to count up the number of significant figures in each of the numbers we're multiplying or dividing, and our final answer is going to have whatever the smallest number of sig figs is amongst those numbers. Now, why is that? Imagine that you want to measure the area of this rectangle. So you get out your meter stick and you say this is 2.49 meters long, and then the width is, let's see, 1.19 meters, and so our area is going to be 2.49 meters times 1.19 meters, and my calculator says that's 2.9631 square meters, but now think about how many decimal places we have. Can we actually measure to a 10,000th of a square meter with our meter stick? We can't. So we're just going to say, what can we measure? Well, we can measure 3 sig figs with this meter stick. As you can see, that's what we got for both sides. We got 3 sig figs. And so we're going to report 3 sig figs here. We're going to get 2.96 square meters. An example of a division problem you can divide these two numbers, and anytime you divide two numbers, you get this crazy long thing in your calculator. I didn't even type this all out. But we don't know that many sig figs. Again, we've got 3 on top. We've got 6 on bottom, so we need to round to 3 sig figs. 1.41 is what we're going to report. Now we come to logarithms. And people tend to have a little trouble with logarithms in particular. And since we do a lot of logs, especially in the last half of Gen Chem, it's kind of important to go through this. Remember that logs are the inverse function of exponential functions, right? So here is a number that has an exponential in it, 6.45 times 10 to the 8th. How many sig figs does this have? Well, this has 3 sig figs. The 10 to the 8th is not really part of our measurement other than to tell us what sort of units we have. So if this were meters, we would say, hey, we've got a 100 megameter measuring stick, something like that. And we measured 6.45 of them. We're going to use that as the basis for figuring out sig figs and logs. Just remembering that this is the inverse function of something times 10 to the 8th. Especially when we're working with base 10 logarithms, this makes a lot of sense, because if the log of something is 2.54, what does that mean? It means that number is 10 to the 2.54 power. What is 10 to the 2.54? Well, it's somewhere between 10 to the 2 and 10 to the 3. So the x is going to be something times 10 to the 2, where something is not equal to 1. Now, if you take 2.54, do 10 to the 2.54 in your calculator, you get this, 346.7 whatever. 3.46 times 10 to the 2, so the log of 3.46 times 10 to the 2 is 2.54. So the 2 tells us it's 10 to the 2. The 0.54 tells us what times 10 to the 2. So for logs, that first bit before the decimal point, that's telling us whatever it's going to be times 10 to the whatever. And so we don't count that as a sig fig any more than we counted 10 to the 8th. We didn't count 8 as a sig fig. So our logarithm sig fig rule is that when you're taking the log of a number, you're going to take the number of sig figs in that number and give the log answer that number of digits after the decimal place. So that might be a little confusing. Let me show you how it works. Okay, so we're going to take log of 59.67. Now this has 4 sig figs. Okay, so I'm just going to say that before we actually even put it in the calculator. When we put it in the calculator, of course, we get this monster of a thing, which is basically 1.7 something. Okay, and now remember what this means. The 1 means that this is something times 10 to the 1, right? 59.67 is 5.967 times 10 to the 1. The 0.7757, all that stuff, that is the part that tells us what times 10 to the 1. So we're going to write this as 1.7758. You'll notice that I had to round that last 7 up to an 8 because of rounding rules. Okay, so those are straightforward calculations. A lot of times, though, we're going to be doing some pretty messy stuff with multiple calculations, as you've seen in our dimensional analysis problems. So let's talk about rules for complicated calculations. And there are basically 2. The first is don't round off and do your sig figs until the very, very end. So do all of your calculations, then go back through, check all of your calculations to see the number of sig figs you should have for your final answer, and then round. The second one is a little more confusing to people, and the second rule says that exact numbers have an infinite number of significant figures. Or another way you can put this is, if you have an exact number, don't use it when you're calculating how many sig figs to put in your answer. So here's an example of a dimensional analysis problem that looks very much like something we did before. And you can see that there are a lot of numbers in here that have significant figures. 10.38 grams, that's 4 significant figures. 63.546 grams of copper, that's 5 significant figures. But what I want to look at is these. 1 mole of copper. Now, a lot of people, when they start out doing sig fig problems, they'll say this has 1 significant figure. 1. It just says 1. It doesn't say 1.00 or anything. It just says 1. But the problem is this is an exact number. 6.022 times 10 to the 23rd is exactly 1 mole. It's not 0.999 moles rounded up. It's not 1.0001 moles rounded down. It is exactly 1 mole. That's the definition of a mole, is 6.022 times 10 to the 23rd. Likewise, you could say for the molar mass, that number we get off the periodic table, in this case 63.546, that's the mass of exactly 1 mole of copper. Exactly 1 mole. So we write 1 mole, and that means exactly 1 mole. It is not something we actually measured. Like I said, we did not actually go through and measure out with a molometer 1 mole of copper. That is something that is a definition. And so if it's not something that you have measured, if it is an exact number from a definition, don't use it to calculate your number of sig figs. Here we have something with 4 sig figs, we have something with 5 sig figs, we have something with 4 sig figs, we have 4 sig figs. Okay, so this is 9.837 times 10 to the 23rd atoms of copper is how we would report this answer. Again, significant figures tell us about the precision of our measurements, and that's really important in science because it tells us how much confidence we can place in your results. If someone asks you how far it is to the moon, and you say, I don't know, somewhere between 200,000 and 300,000 miles, like how much do we trust that? We don't trust it very much, right? If someone has actually measured it with greater precision, which people have, so they might say, you know, the closest it comes and the farthest it comes, you know, you can get more precise measurements. How much we trust the conclusions people are making based on their measurements depends on how precise their measurements are. And so using significant figures to represent that helps us to understand how much we trust our numbers. I hope this was helpful, and I look forward to seeing you again soon.